Hello and welcome to the C programming lecture on creating libraries. Now, what is a library? In a broad sense, a library is a collection of code that can either be used by the preprocessor to include the code, or it could be linked with during the compilation time of a program. So what this really means is that there's certain methodologies in how to create a library. Now, in certain contexts, we will be explicitly talking about how to link against a particular library. So some of the early methodologies of compilations have been carried on throughout the years. However, nowadays, certain methodologies don't make as much sense. So that's kind of why I bring up this point where you could just include the code rather than compile it. So, and have individual translation units that are linked together. Now, that statement may not make sense right now, but basically you will see over the course of this lecture some interesting pieces that you may yourself question why this is being done. So this is the standard way that most C programs are created. In C, the standard way of compiling a program is usually broken down by generating something called object files per each source code file. This means that every extension, for every file that has a .c file extension, an object file is typically generated for that piece of code. At the end of the compilation process, the linker's job is to link all of these object files that were previously created in order to create our final executable. So, what are object files? So object files is really just a relocatable format of machine code. So it's not an actual executable, but it is a translation unit or some type of chunk of code that you can think of that is able to be linked with at compilation time. Usually in Linux, these object files will have the .o extension. So here I'm showing you the standard way of creating basically a library that we will later link with. So on my very far left, I have my main program. You can see that I'm including a header file. This header file includes a structure and also the prototypes of particular functions that I will be using. So I'm creating a vector2. And then I'm also calling or invoking the function print vector, which is defined inside of this prototype. So this is important. My program still needs to know prototypes, so I still have to include this particular code in here, which makes sense when we think about it because our stdio, when we went back into the preprocessors statements and how our include directive actually just copies code over from that particular .h file, that header file, all we saw was prototypes. So again, since we're going to be using a library, we at least need to know the structures and the prototypes at minimum. So on the very far right, we can see that we actually have the implementation of this code. So we have a magnitude plus a print vector. And we can see that particular code is, we are only calling the print vector, but the print vector function actually calls the magnitude function. And you can see the output here. So here is the standard way of compiling the program. You can see here I have a few arrows that are showing you and highlighting what has actually occurred. So this first line here, we are compiling, and this .o flag signifies that we want it to be the actual .o file with the c dash lowercase c. So you can see we compile this vector2.c file. It actually produces our .o file. Next, we're going to compile our C file. You can see here it creates a main.c file. Now what we're going to do is we're going to link these two .o files together by feeding each one in. And since we're using the math library, we need to include this -lm to say basically include the math library in our linking. And you can see that finally we have produced our actual a.out executable. Now, this a.out executable actually produces this output. So we can actually execute it. Here's all the files you can see in order. And again, you may be wondering, for this small of code, why does it even make sense to do this? And that's a great question. So Again, this is just how things were done previously. Typically, people say this was done because of memory constraints. File sizes and available memory in the past was much more limited than what we have today. So perhaps compiling in this manner made more sense. But nowadays, depending on your thought process, this may not make as much sense. And there's no real benefit to doing it one way or the other. Those are opinions that you can develop on your own. Okay, so within these library types, we need to talk about basically what we did before was basically take translation units, which were .o files, and then compile them together. Now there happens to be a different way to do this. We have one way, which is called static libraries. So a static library is really just a collection area of ordinary object files. So kind of like how we did our process before. However, sometimes this static library will include hundreds of compilation units. So hundreds of .o files or something along those lines, lots of them. So in order to do this, we basically use another tool called rn, and we have some flags rcs with the library name .a, which is the typical extension, and then we list all of our object files. So again, these static libraries can be fed to the compiler during the compilation process in order to have the linker patch the main executable with the code that we are calling located inside the static library. So here again, we're using the same exact example from our other program, where we have a vector2i with some implementation details here. So on the left is our header, on the right is the implementation, and then we have a vector2f, similar thing here. Now, what we're going to do is we're going to actually compile both of our O files. You can see that I list out all the content of this directory. We only have C and H files. We compile this vector2i.c or vector2i.c file and the vector2f.c file. And then what we do is we use our actual archive utility to create our static library. So you can see that we can have a bunch of different O files inside of a static library. Now, let's go ahead and try to use this. And what we're going to do here is we're going to create two different variables. We're going to have a VI, which is a vector2i, and a VF, which is a vector2f. And they're basically doing the same things. Again, if you're having trouble following along, don't worry about it. This is just details that you need to understand at least how this stuff works. And if you would like to, usually it's better to pause the videos, write the code out from the prior slides, and continue on with these examples. So, all right, so what we're doing here is, like I said, we have some variables, and then we're calling these functions which are defined inside the H files. The H files were on the prior slides before. We showed them with the implementation. So we recall that we created our .a file, which was a collection of .o files. Our .o files were the compilation units, the translation units for the vector2i and the vector2f libraries that we created, the .o files. So we can see here when we compile our code, we say gcc main.c, and we just pass in this particular our static library. The lm is again for the math library because we use the magnitude function, which consequently uses the square root function inside of the math library or the C standard library. So we have to link against that. And you can see when we actually, after we compile, we can run our program and we get the expected output. Okay, so the next one is a little bit more confusing. Now, we have something called standard shared libraries. We have static libraries, which is what we covered, which are just compilation units just packaged up nicely inside of a .a file. And then we have something called shared libraries. So shared libraries are sometimes referred to as dynamic libraries. In Windows, the extension is .dll, and then the other one inside of the other extension inside of Linux may be .so. So shared libraries are dynamically linked into a program during the runtime instead of compilation time. So that means that your code is patched in when that executable is about to run. Code is patched into it right as it starts to boot up. So the details, how the system loads dynamically, are a bit beyond the scope of this course. However, it's a great thing to conceptualize. So we're going to recompile our statically linked program to use a dynamically linked library instead, or a shared library instead. All right, so there's a few weird things that you may run into, and one of which is all of these flags. If you want to know what each of one of these does, I suggest that you just look inside the man page or read online, because GCC just has so many flags and so many options, it's hard to kind of parse through. And honestly, like, it changes from some platforms to others. And as long as you're following along this course and you're using the Debian image, it should be relatively the same. Okay, so what we're going to do now is we're going to take our C files, and we're going to produce O files that are capable of creating shared libraries with, right? So the first thing we're going to do is we're going to create our, right here, we have our vector2i C, and we're going to create our O file. The next thing we're going to do is we're actually going to create a shared library from that O file. So right now we're only using our vector2i. Now we could use vector2f as well, but in this case we wanted to keep it simple. So you can see that our flags changed quite significantly. To create the shared library, we need to pass the shared flag with the .o, the name of the shared library, and then here is the .o file that we previously compiled. All right, so here's an example of using that particular library that we created. You can see that I include the header. Inside this header, below is the actual implementation details here that you can see. Now what we're doing is we're compiling this program by saying basically, okay, link with whatever is in this current directory. Here is the name of the file that we need to link with. We need to link with the math program as well, because we're including the math.h header. And here is the name of our program. So it compiles, we run the program, and everything works. So it's going to look for this particular file in this directory. So if we move the file out, this program will probably fail to actually run. Now there's other things that may occur, and there's a whole pool of information as to how this stuff works. Again, it's not particularly important right now. I just want to show you some of the basics. Okay, so I want to show you an example now of swapping dynamic libraries. So this is what we're going to do. We're going to, you can see here, we have basically the same exact setup here, except we edited our v2i print vector, and we just simply, instead of outputting anything, we just simply had this particular program just print that it's not implemented. Okay, so what does that mean? So when I recompile this .o file and I recreate this shared library using the same names as previously, but I do not recompile my actual program, you can see when I execute that program, it actually executes this new code. So you remember how I said that at runtime, it will relink with whatever the dynamic library is that you have specified. Now, this is an example of this occurring. There's alternative ways to do this, but this is one way of doing it. Okay, so the other way to do it is dynamically loading libraries using specific code. So loading a dynamic library can actually be called explicitly within code. The steps to do this are platform dependent. So in other words, the standard library doesn't actually provide a default way of loading a dynamic library. Once a library has been loaded during runtime, it can be checked for a particular function, usually called a symbol, and we can also retrieve a function pointer to that particular function we are searching for, as long as we know the signature. So the compilation process for this example is similar, but we do not link with the library during the compilation process. So again, here's an example of this. Here is our, on the right, or is our actual main program. On the left is the actual vector2 example that we've been using this entire time. And you can see that the actual checking of these functions has gone up. Like you see things like a void pointer now, and this weird function call called dlopen. And now we have another include statement, which is dlfcn.h. So these functions allow us to attempt to open up a particular shared object file and read into it and check for particular symbols. So you can see that on line 15, we check if it's nil or null. It will go ahead and print out what failure has occurred. If it exists, then it will check to see if we have a v2i print vector, which we should have, and it will store that function pointer into our prior function pointer here. And then inside of this, we check to make sure it's not null, because we don't want our function call to cause a segmentation fault. So we call our print vector function pointer, and then we just close out the library. So this particular piece of code is better something that you mess around with. It's a bit obscure how this works, but when you think about it, you can create potentially some type of hot reloading situation during the runtime of a particular program. Now, some people may say that's dangerous and you shouldn't do that, but it's good to experiment with this stuff and just figure out, how these things work and how you can benefit from potentially, using some of these functions. Okay, so here's an example, that prior code of it actually running. So again, we'll kind of flip back and forth. You can see this as calling from lib and the magnitude and the output. So again, down here, we see that we say calling from lib magnitude. And again, this is the actual program on the right. So when we call it here, print vector function, which is checking for our v2i underscore print underscore vector, that's actually calling this on line 12 for our file vector2i.c. But remember, it's actually loading this shared file that we compiled previously. So it's kind of an interesting concept. All right, brief review. I know that was a lot of information kind of poured out into a short period of time, but I just need to at least expose you to some of this stuff. We're going to go through some coding examples, but try to keep it as simple as possible just because there's a lot of information in this. So the most common way people compile code is one file at a time. This produces our object files. That's an important distinction. Like either you're using shared or non-shared, you have to produce object files. There are two different types of libraries that we got, static and dynamic. Static libraries are built into the actual program and cannot be changed without recompiling the program again. The dynamic libraries are loaded in at runtime, and they can be loaded by platform specific code that checks for a particular library and a particular function, also known as a symbol. So I want to point out that this alternatively, you can do something called a Unity build. Now, Unity build is not referring to the game engine Unity. A Unity build is simply just an idea. It's very simple, as you just include all of your code at the top and headers, because you have the typical memory constraints in the past did not allow you to include thousands of lines of code because you didn't have that much memory inside your computer. But now, at the age where we have several gigabytes worth of memory, this isn't really an issue, especially if you're working on something relatively small. It actually runs a lot faster, the compilation time, and you can just try this out for yourself. Write a fairly large program and try to do different ways of compilation. Really, when you stop and think about it, and through my actual experience, anytime I've ever needed to actually change a library, especially if I've had a dynamic library, usually most changes are breaking changes. So I usually end up having to recompile the main program as well as the dynamic library. Very, very rarely, unless it's like patching something that had a bug, would I need to only update the dynamic library. And consequently, if you use a static library, you have to recompile anyways. So again, this is food for thought. Trying to not make this an opinion piece, just experiment with these different things and come up with a way that suits your needs. Okay, let's go ahead and just start out with the static library compilation process. And now throughout this code examples, we're really just going to go over the static and dynamic, just so that way you can get your hands kind of dirty with some of this stuff. So first and foremost, we're going to go ahead and just create our actual program, and we're going to do our typical hello world deal. Make sure everything's working. There we go. All right. So now what we'll do is let's create another file. Let's just say this file's name is, let's just say library.c. And inside we'll also create a library.h. And let's go ahead and open up this guy. And let's think about what we want to do here. So maybe we don't need stdio.h in there. Instead, maybe we need it here. Let's just do this. We'll say this is void. Just print. It's like we'll just say greet, and then maybe we take in. No, we'll just leave it like that. Yeah. Hello. Real simple. Simplest case. So we have this is our header file. So what we can do is actually let's open up our C file here. We'll take this guy and then copy him, paste, copy that guy, go back. There we go. So we have a function which is name greet, right? And we're going to just print hello. Fairly simple. We don't need anything complicated inside of here to prove our point. So inside of our main.c file, so what we'll do is just pull this guy over, keep these two separate for now, and we can actually just put him down here. So that way you can see the implementation details. And what we're going to do is we're going to include our library.h. And recall when we include in the current directory, we need to have it around quotations, because that means to the compiler this particular header will be in this particular folder, or more thoroughly, it's actually going to be inside of our include location. All right, so we have that, and now we can call our function that we declared over inside of our library.h file greet. Okay, so now what we're going to do is we are going to create our .o files. So how do we create our .o files? So if you recall, what we're going to do is we're going to say gcc-o-c, and then we'll pass in the name, which is library.c. Compile that, gcc-o.c, main.c. And now what we're going to do is compile. We'll list everything out. So we already have an a.out, which was previous. So let's go ahead and let's create our new a.out, which will actually call the function greet. So right now it's just hello world, because that's what we did at the beginning. But what we're going to do instead now is we're actually going to link these two .o files, our library.o and our main.o together, in order to create our new a.out file. All right, so GCC, I want to pass in main.o, and then I want to pass in library.o. And we can just hit enter, because we don't need to link with anything else, or we don't need to list out any more object files. And let's go ahead and run that, and we can see that it's calling our printf function inside of our other .o file. So again, using the static library method is basically the same whole process, except that we are creating a actual a actual archive by, you know, the .a extension. Now, in order to do that, basically, since we only have one .o file, it should be fairly simple. Let's go ahead and remove our a.out file, and let's just create a archive. So ARACS, and then we're going to pass in the name. So let's just say library.a, and then we'll pass in the actual library.o, which is the name of our the prior .o file compiled from this particular library file. Hit enter. We should see the .a file in there. And now what we should be able to do is actually link now our main.c program with this, in particular, this library.a, right? So, and now we can run it, same result. Again, there's nothing really special going on here, and it's not that much different than just passing on our O files. It's just a convenient way to package up a bunch of open O files. So in our next example, we're going to go through the dynamic library, pretty much using this exact same code, just not actually using our archives or our static libraries.